In this lecture, we will discuss natural homomorphism. Natural homomorphism. So, for defining natural homomorphism, we have one theorem. The statement of the theorem is let G be any group. G be any group and N be any normal subgroup of G. Normal subgroup of G. Let F be the mapping from G to G over N or G by N, defined as Fx is equal to Nx for every x belongs to G. So then F is a homomorphism of G onto G over N, and the kernel K is equal to N. So kernel K, or we can say that kernel F, is equal to N. So now this is the statement. So now we prove this theorem. So we shall prove this theorem. So we consider the mapping which is defined as G to G over N. So N is a normal subgroup of G. Of our quotient group, N work as a identity element. So you remember such that function is defined as fx is equal to nx. So for every x belongs to G. So we can say that let nx be an element, any element of G over N or G by N. So then we can say that x belongs to G by using the quotient definition, quotient group definition. We have a function which is defined as fx is equal to nx. So which is defined as fx equal to nx. So we can say that fx, that means function is homomorphism of G onto G there, G by N. So because function fx is equal to nx, so that means nx. So G by N having the preimage in G. So this is defined as G onto G by N. So we consider therefore f is onto G to G over N. So now we shall prove that function f is a homomorphism. So we shall prove that first thing is function f is homomorphism. So proving function f is homomorphism. So homomorphism condition we have that. So for every a and b we take as belongs to G. So f of ab, which can be written as n of AB. So we take as fx equal to nx. We take two elements, that is AB belongs to G. So that means when AB, write down AB and by using the definition, so this can be written as n of AB. So n of AB, that can be written as NA into NB because n is a normal subgroup. So n is a normal subgroup. So when n is a normal subgroup, so again we use the definition. So Na can be written as Fa and Nb can be written as Fe. So Fab is equal to Fa into Fb. So we can say that function f is homomorphism. F is homomorphism G onto G by n or G over n. Now for proving onto, so it is obvious. So every we can write down directly every quotient group of a group is a homomorphic image of the group. Homomorphic image of the group. So that means when we define the mapping G to G over N, so such that fx is equal to fx is equal to nx. So fx equal to nx. So for every x belongs to G. So x belongs to G. So that means this term. So because this is f is onto, so f is onto, so f is onto. So we can say that this function, this function f from G to G over n and defined as fx equal to nx. So this is called natural mapping. So is called, we can say that natural mapping. So this is called natural mapping. Natural mapping of G onto G over N. Natural mapping of G onto Gn. So now the third thing we will prove that means kernel K is equal to N. So for proving kernel K equal to N, third, to prove that kernel K is equal to N. So for proving kernel K equal to N, we write down as let K be a kernel, K be the kernel of homomorphism, K be the kernel of homomorphism F. So we know that we know that the identity element, identity element of quotient group, identity element of quotient group G over N is the coset, and we have already proved this thing. So we can say that K, kernel K is equal to, we can take as Y be an element which belongs to G, such that f of Y is equal to N. So by definition of kernel, Nk equal to E, f of K equal to E, N work as a identity element. So we can write down as Fy is equal to N. So now by definition of f. So what is the definition of f? So definition of f is say that fx equal to nx. So here we take element k. So f of k can be written as n of k. So we use this definition f of x equal to nx. So we put f of k is equal to nk. So f of k equal to nk. So for every we can take as k. So k belongs to K. So now we can say that nk. So when we take nk, so nk is equal to, we can write down as n. So nk equal to n, so which implies that k belongs to n. So k belongs to n. So here for every we can write down as k belongs to capital K, but we have proved that k belongs to n. So how to prove that? So by using the HH is equal to H. So this H or belongs to H. So we remember this theorem. So when nk equal to n, so this means that small k also belongs to n. So we take the element k, small k, which belongs to k. So we write down as this k, which belongs to k. But now this k is the element of n. So this we can say that uh, k is the subset of n. So all the element be the element of n. So we can take as equation number 1. Now, again we take the element. Again we take the element of n. So let n belongs to n. So we take the element of n which belongs to n. So this can be written as, so that means nn is equal to n. So when n belongs to n, so we can write down it hh is equal to h. So nn equal to n. So now by definition, so now we have a function of n. So now we take as n, f of n. This f of n can be written as nn. By definition, f of n equal to nn, or this nn is equal to n. So this nn equal to n. So here we see that this n. So when we take as a fy, so this y belongs to g, fy equal to n, so this y belongs to k. So here fn equal to nn, or nn equal to identity. So it means say that this n belongs to capital K, which imply that n belongs to capital K. So by definition of kernel, we have the function of x, fx is equal to e. So e means n work as a identity, or x be the element. So that means x belongs to k. So it means that x belongs to k. So here fn equal to identity. So it means that n belongs to k. So when n belongs to k, so here we take small n be the element of n, but this implies that small n belongs to k. So it means that all the element of n is also a element of k. So it means that n is the subset of k. So this is our equation number 2. So from 1 and 2, so we can write down from 1 and 2. So n, first is k is subset of n, or here first k is subset of n, or here n is subset of k. So all the element of k belongs to be the element of n, or all the element of n be the element of k. So k equal to, it means that k equal to n. So kernel k is equal to n. So we have proved this.